Good morning to all our viewers. I'm Dr. Balvinder, your moderator today. Welcome to the National Institutes of Health, NIH, Continuous Medical Education CME session for 2024. The NIH CME is a series of online webinars which provide a platform for NIH researchers to share their experience, expertise, and make available the research to others. Today's CME is the fifth of a series of 6 sessions for the year 2024, and this series will be hosted by IMR. IMR is one of the 6 institutes within NIH which conducts biomedical research as well as provides training, consultation, and diagnostic services. As for today, we have our special guest from IMR, Dr. Sarbhan Singh and Dr. Nur'ain, who will be sharing their experiences about modeling infectious disease using mathematical models. Before we begin, we shall present the IMR corporate video.
The Pathological Institute of Kuala Lumpur was established in 1900 by the Resident General of British Malaya, Sir Frank Swettenham. Its aim was to promote the health status of the local population and to explore the great and unknown field of tropical medicine. The institute was renamed as the Institute for Medical Research, or IMR, a year later. Initially, the focus of its research was on beriberi and malaria. Subsequently, its scope expanded into the causes, treatment and prevention of a variety of other tropical diseases such as cholera, smallpox, leprosy, tuberculosis, typhoid, filariasis, dengue, melioidosis, scrub typhus, and nutrient deficiencies. With independence, the IMR became the research arm for the Ministry of Health Malaysia, where research conducted has been aligned with the country's health research priority needs. In more recent times, research at the IMR has progressed to gathering in-depth knowledge of allergy and autoimmune diseases, primary immunodeficiency diseases, and through the development of allergy test kits. Cancer research at the IMR has vigorously looked at diagnostics, prevention and early detection, as well as identification of novel biomarkers and targeted therapy for precision medicine. For this, the Institute has been equipped with a specific pathogen-free or SPF animal facility and biobank. The IMR has developed its expertise in nutritional biochemistry, where there is active involvement in preclinical studies on metabolic syndrome, diabetes, cardiovascular health, and endocrine-related diseases. The Institute's iodine test kit is used nationwide for monitoring under the Iodine Deficiency Program. The dawn of the next millennium saw many issues that were related to contaminants and pollutants in the environment and in the workplace and its impact on human health. Thus, in a forward-thinking manner, IMR conducted vulnerability assessment on impacts of climate change on health and health delivery. Malaysia is in a region that is full of biodiversity. The Institute has a unique interactive e-database called GlobinMed, which strives to become a referral source on traditional and complementary medicine, or TNCM. The Institute steadily has been moving towards drug discovery programs. The Center conducts preclinical safety evaluation of herbal extracts under Certified Good Laboratory Practice or GLP conditions, assessing efficacy of herbal products using in vivo as well as in vitro systems, phytochemical analysis, and structure elucidation. The IMR has continued to provide in-depth research related to infectious diseases, especially during outbreaks, and it is the reference center for Zika, dengue, influenza, leptospirosis, and melioidosis. IMR is the leading center conducting Wolbachia research in Malaysia. The Institute has equipped itself with a BSL-3 laboratory as a preparedness plan for any possible future outbreaks. Epidemiological research activities have helped to establish the distribution of diseases, its factors, and how it helps in controlling diseases. The IMR provides specialized diagnostic tests nationwide related to organ and blood stem cells transplants, diagnosis of inherited metabolic diseases, inborn errors of metabolism or IEM, genetic diseases, and multiple myeloma. In the international arena, The IMR serves as World Health Organization or WHO regional and collaborating center for infectious and tropical diseases. Under various programs, the IMR has produced a few patented products ranging from insecticides, fungi, dengue, chikungunya, saliva and forensic test kits, mosquito detector and trap, paint, anti-cancer toxin, and many more, from which some of the patented products have been commercialized. The 116 completed years of the Institute's illustrious service continues with new challenges and higher pursuits as the IMR transforms its biomedical facility to support research both nationally as well as internationally. IMR to be a world-renowned institution for biomedical research.
Welcome back to our CME. And without further ado, I would like to invite Dr. Nur'ain to deliver her presentation on time series modeling.
All right. Thank you, Dr. Sarbhan, Dr. Balvinder, for the introduction. Assalamualaikum warahmatullah, and a very good morning to all the viewers. First of all, I would like to say thank you for joining our CME session for today. Without further ado, we shall go to our slides for today. If you look at the content in the CME, we will learn about why we model and forecast. We will go through some of the models under time series modeling, and also some of the model under compartmental models. And subsequently, we will learn about how we develop and validate the R value algorithm and some of the achievements that we've done during the COVID-19 modeling outputs. So, firstly, why you model and forecast? Currently, we are dealing with many infectious diseases. You have dengue, you have TB, influenza, and 4 years ago, we have to deal with COVID-19 pandemic. So, from this infectious disease, we know that we need to have a very good surveillance systems. But our current surveillance system is quite passive in nature, and hence there's a possibility of delay in reporting. So how modeling can help in overcoming this limitation is that when you model a data, you can it enables us to do a forecast of cases, and this forecast can be used to make an early warning system. And when you have an early warning system, you can use that to make a proactive intervention, a public health intervention. So now we go how we can use time series model to model infectious disease. I think it's very important for us to go into the basic of time series data. By definition, time series data is data which are collected sequentially at regular time intervals over a period of time. So the frequency of your time series can be in minutes, in hours, daily, weekly, monthly, or even yearly. If you look at the figure, it's actually it's a sample of time series data which I got from the Ministry of Health Malaysia COVID-19 Public GitHub that shows the national daily confirmed COVID-19 cases from 7th of August to 5th of October 2022. So from this time series data, you actually can plot into a graph, and whereby the x-axis will show the time variable and the y-axis will show you the number of COVID-19 cases. So basically, this is a very simple example of a time series data. Once you have a time series, you can actually identify 4 important components under the time series. So the 4 components are the trend, the cycle, the seasonal, and the random events. Trend is defined as a long-term increase or decrease in the series, whereby if you can see, if you look at the graph, this graph actually shows a very good downtrend time series. If you look at the graph, yeah. Then cycle is a rise and fall with no fixed frequency. And when you look at the graph over here, you can see that there's two obvious cycles. The first cycle is from 1975 to 1982. So it's around 7 years of cycle. And the second cycle started around 1982 up to 1992. So there is a 10 years of cycle. So cycle by definition has no fixed frequency. So as you can see in the graph, the first cycle lasted for 7 years and the second cycle lasted for 10 years. So there's no fixed frequency. In contrast, seasonal over here is a regular pattern with fixed frequency and recur every calendar year. The graph shows a very nice seasonal trend over there where you can see the peak of the cases occur every mid of the year from 2011 to 2016. And you can see the pattern is very regular throughout 2011 and 2016. So this is a very nice graph of a seasonal data. And the fourth component is the random events. It's basically just a random fluctuation in your data series. I would like to emphasize that each of these components is not exclusive, meaning that this component, a few of a component can occur at the same time. So within a same series, it can have combinations of different components. Imagine this is your time series data. This is the original time series data. You can actually decompose it, means you dissect all these important components into its individual components. And once you dissect it, you can able to see this is the overall trend of the series, this is the seasonal part, and this is the random fluctuation. So by knowing all this composition, you can identify each of the individual components. So why is it so important for us to identify these components? Is because by doing so, this component can be used to model your data. So how you do it? You can use the decomposition method. Under this decomposition method, there's three main model, which is the simple exponential smoothing, the Hold's linear trend, and the Hold's winter seasonal. If your trend, if your overall time series has no trend or seasonality over here, basically you can model your data using simple exponential smoothing. This is actually the mathematical formula, but I will not go through it. So if your data has trend component, you can use Hold's linear trend. And if you can see the formula over here, you see there's a trend equation that actually capture the trend components in your data series. And say that if your series has trend and seasonality, you can use Hold's winter seasonal. And when you can see at the formula, you can see that there's a trend equation and seasonal equation that able to capture both the trend and the seasonal components in your data series. Okay, what is so interesting about time series data? Most of the time series data, not all, but most of the time series has autocorrelation. And what I mean by autocorrelation is a representation of a linear relationship between a point at a given time t and its lag value, where k refers to the lag time. So if you look at this statement, I can say that we can actually use this previous time lag that has a significant correlation to the time t to forecast your future value. And how would you know whether your data has autocorrelation? You can actually use the autocorrelation plot. This is an example of an autocorrelation plot. Let me explain what this plot is about. So basically, this autocorrelation plot shows autocorrelation between its time variable and its lag value. If you look at the x-axis over here, is the x-axis. This shows the lag time. If at point 0 it's basically lag 0, then you go to lag 1, lag 2, lag 3, up to lag 10. The blue shaded area is the 95% confidence interval. So how would you know which lag value has a significant correlation with the current time point? Is actually by looking at the lag value that exceeds the blue shaded area, the 95% confidence interval. So in this example, we can see that lag 1 has a significant correlation. If you look at the other lags from lag 2 to lag 10, it actually falls within the 95% confidence interval, so it does not have a significant correlation. So if I have a lag 1 correlation, what does it mean? If you look at this timeline, you say that I have data which is has significant correlation at lag 1. If you have a data at t-1, you can use that data to forecast your value at point t. If you have your data at point t, you can use that data to forecast t+1, so on and so forth. So that's how autocorrelation works. So under the umbrella of autocorrelation, if your data has autocorrelation, you can use autoregressive method to model your data. And under this umbrella of autoregressive method, you have 4 different models that you can choose. The first one is the autoregressive. Second one is moving average, autoregressive moving average, and autoregressive integrated moving average. How do you want to choose this model? Which one to use? Which one is best fitted for your data? You can use the autocorrelation plot and the partial autocorrelation plot. So this is how ACF and PACF graph looks like. So actually there's a way on how you want to read this to identify which model to best fitted for your data, but I will not go through it because it's actually a course by itself. Okay, in third situation, say that if you have a X independent time series which has a linear relationship with a Y dependent time series. So you can use this X series to actually predict your Y series. If you have one predictor, you can use simple linear regression. And if you have 2 or more predictor variables, you can use multiple linear regression, as simple as that. However, not all data are has linear relationship. So if your data has a non-linear relationship, you can actually use exponential model. You can use even polynomial model. And with recent years, we have all those machine learning techniques. You can even use all those artificial neural network, such as the LSTM, the GRU, and the convolutional neural network. So in short, I can summarize that under the time series model, you can have 3 major models, basically the decomposition method, the autoregressive method, and the regression method. Which one to use? Well, all the models are very good, but then how you want to choose, it all depends and it falls back to your data. Which one, you have to look back, you have to dissect it, you have to know which component actually exists in your data, and you choose from there which one best suited your data series. Okay, once you have fitted your model, I'm sure you will wonder, like, how good is my model? How you want to assess your model? You can use goodness of fit. So what is goodness of fit? Goodness of fit is basically assessing how well your regression model fits the observed data. It reflects the proportion of variation in your forecast variable that is accounted for by the regression model. So the goodness of fit, the term that we use is R square. It varies from 1 to 0, 1 being the best fitted model, the best fit, and 0 being the poorest. And if you look here, this is actually the formula, but I will not go through the formula. I will simplify it by showing you this graph. All right. So if you look at this graph, imagine that you have 20 time series data points, and you can look at it is from point 1 to point 20. There's 20 blue dotted observed data. And the black color line is the best fitted model. So if your best fitted line falls exactly on top of the observed data, you can say that the goodness of fit is 1 because it falls exactly on top of the observed data from point 1 to point 20. If you have another model that fit the data but it somehow deviates from the observed data, you can see that the goodness of fit value will fall below 1. So other than R square, you can also use other metrics such as the standard error regression. You can also use a Kaiki information criterion and the Bayesian information criterion. Either one is actually, it has its own strength and limitations, so you have to choose which metrics actually best to assess the goodness of fit of your model. All right, now I'd like to share how you can, some of the strategies that we can use to improve our model. All right, in real life, in real world, most of our data are very noisy. And what I mean by noisy is you can see a very random fluctuation in your data. If you look at this is an example of a very noisy data where you can see a very high amplitude zigzag appearance. This is what we call a noisy data. What's the problem with noisy data is when you try to fit a model using a noisy data, it will interfere with the model estimation. So your coefficient is quite hard to, the model estimation will be interrupted due to this noisy data. So how you want to overcome this limitation? You actually can smoothen your data. So how you want to smooth it? You can use central moving average to remove all this noise. So over the right side is an example of how actually we actually applied central moving average towards this noisy data, and it transformed into this more smoothened data over the right side. So if you look at it, it's more smoothened, and you can see this model fit. You can see the line is more smoothened. So your fitting actually gets better when the data is actually more smoothened. This one I would like to emphasize that if you want to smoothen your data, you should not overdo it, because sometimes when you overdo it, say that, for example, you make a comparison within this 3 moving average and 9 moving average. So if you use 3 moving average, the underlying trend is still, you are able to, it still exists, the trend is still there. However, if you overdo it, you're just going to get this straight line. So it will obscure, it will remove the important components behind your data. So I would like to re-emphasize not to overdo your data smoothing. Strategy 2, if you have additional regressors that has significant correlation with your response variable, you can actually use that regressors as a covariates into your model. So this is an example that we did before. In this study, we actually forecast the model using the ARIMA model, and we use weather data as a covariate to forecast the dengue cases. And it happened to be additional of weather covariates is actually forecast the dengue case better than having only the dengue cases in the model. And this is another model that we established where we use assemble ARIMA models to forecast dengue cases in districts, I think 7 districts in Selangor, whereby we did use neighboring districts' dengue cases to make a forecast in one particular district. This shows a better forecast accuracy when you incorporate this neighboring region's dengue model. So now I would like to just share 2 of our projects that we have done previously using time series model. Both of these projects were developed during the COVID-19 pandemic. So the first project, we did it during the second wave of COVID-19 Malaysia, in COVID-19, and we used ARIMA models with some covariates to forecast 14 days daily COVID-19 cases. We actually applied the strategy of data smoothing, and we used 3 different covariates, which is the active cases, state and district cases, and neighboring data. So this is our first project that we developed during the second wave of COVID-19 using time series. And during the third wave of COVID-19 in Malaysia, we developed another ARIMA model where we use different types of covariates to forecast 28 days daily COVID-19 cases. So as before, we actually use data smoothing, and we use subnational, which is the state cases, to forecast national COVID-19 cases. And we actually use more data points because it's already the third wave of COVID-19. However, we face a few limitations. We noticed that this ARIMA model are unable to make long-term forecasts. So if you look at this graph over here, This is the blue shaded area is the confidence interval. So if you can see, as the longer forecasting horizon as the forecasting horizon lengthens, you can see that the confidence interval widens up. So meaning the accuracy of the data, the accuracy of the forecast actually becomes less accurate. So we see that one of the limitation is we are unable to make longer term forecasts using ARIMA model. The second limitation that we noticed that we were unable to determine the appropriate disease parameters because we are unable to incorporate all this R value. And the third limitation was unable to model disease dynamics, which say that we cannot incorporate the effect of non-pharmacological intervention, and at that point of time is the intervention of movement control orders and also in vaccinations. So due to these limitations, we thought of coming up with a different model, which is the compartmental model. So this will be given by Dr. Sarbhan, but I will pass back to Dr. Balvinder first. Thank you.
Thank you, Dr. Nur'ain. That was a very, very interesting presentation. There's so much of information on how these models are actually created and the ARIMA models. In fact, I think I learned a lot from your presentation itself.
Thank you.
And well, after ARIMA models, in fact, when we were doing our modeling for COVID, we had to move on to something even more complex, but it would actually solve the limitations which we had with ARIMA. So, and with that, we actually moved on to compartmental models, and for that, we have Dr. Sarbhan, who will actually give us a presentation on compartmental models. To you.
Thank you, Dr. Balvinder, and very good morning to all our audience here today. So, Dr. Ain has already spoken in great depths of time series models when it comes to infectious disease. And now I would like to just share a little bit of our experience, which we have done, modeling using compartmental models. But before that, let me just make one thing very clear. If there's one important take-home message that you should take from what Dr. Ain has mentioned about time series model is essentially that it's a type of model that uses past observations to actually generate future observations. Now that is the distinction. So well, having said that, how is compartmental models different from time series models? Well, let me just show you this diagram. Right. So compartmental models are also known as deterministic models. So inherently we see a glaring word here known as compartments or compartmental. Why? It's because this model essentially is generated by using several compartments, right? So if you look at this diagram here, we have got 4 compartments, which is labeled as the susceptible, the exposed, the infectious, and the removed. Now, each of these compartments essentially represents people, human beings, and how they move along with a particular disease or a particular infectious disease. So let's just wrap our head around this. To start off with, we have a susceptible compartment, or we also call this as a state variable. So susceptible compartment means what? Whoever or whichever people who are in this compartment have the likelihood of acquiring a particular infection upon being exposed, right? That is what is here. Now, once they have been exposed, these individuals then will move down to the next compartment, and they are now considered as individuals who were previously susceptible and are now have been exposed. Now, at this level here, what is important for us to note is not everyone who is exposed would develop an infection, right? Not everybody who is exposed would develop the infection. There would be a certain number or proportion of them who will become infectious, and this is actually determined by something as we call as the infectivity rate. Now, so bear in mind, these people in the exposed compartments, they traditionally would not have any symptoms upon exposure, and the moment they start developing some symptoms, okay, Normally when the incubation period is over, they start exhibiting some symptoms. That is when they have already moved from the exposed compartment to the infectious compartment. So now they are already actively having symptoms and they have the pathogen in them. Now what should happen next if you look at this model is these infectious people will then transcend down to the last compartment, which is known as removed. Now this removed compartment can represent several things. It can either be they are no longer infectious because they have been treated, they have been cured, or they actually succumb or they die due to the infection. So they are now considered removed and they no longer contribute to this compartment. All right, so in essence, if you can appreciate this, you can clearly see that compartmental models are not looking at observed trends or past trends. Instead, they are actually factoring in the disease dynamics and its transmission through several state variables or several compartments to provide you a forecast. So what you see here is essentially all the rates that are being put in place, because we need a rate to determine how individuals are going to move from one compartment to the other. And the first rate that determines how susceptible people move to exposed is basically the likelihood of disease transmission. From infectious to removed depends whether you are using removed here as recovery rate or death rate. You set your rates. And how is it we identify these rates or these parameters? Well, there are several ways of doing that. One, we can analyze it using whatever available data we have or whatever available rates that have been reported in literature. Or we can also allow the model to actually calibrate and identify certain rates. So this is basically in a summary of how compartmental models work, right? Okay, now my subsequent slides, basically I'm going to share with all of you all how we here at IMR has actually used compartmental models to model COVID-19. So COVID-19 is actually the infectious disease at question here. So we initially started off with a compartmental model called extended SEIR model. So SEIR model is the model that I've showed you earlier, where it has got 4 state variables, which is the susceptible, exposed, infected, and R. Now, why do we call it extended? We call it extended because in addition to the conventional SEIR model, we had added several other state variables to represent the disease dynamic a bit more better. For example, under the exposed component, we factor in another 2 state variables such as those individuals who have been exposed and were quarantined, and exposed but were not quarantined. Similarly, infectious, isolated, infectious, not isolated. So why did we do all of this? So we did all of this essentially to make the model a more holistic model that could represent the disease dynamics as closely as possible. So what were the strengths of this model? So this model enabled us to determine several parameters. What are these parameters? These were the rates that I've mentioned earlier. So and if you can look at this table here, this is the paper that we have published from this model. So you can see, as I mentioned earlier, all these parameters here are the parameters that essentially determine how individuals move from one state variable to the other. And you can see that these are the values. And where did we get the values? Basically, we got the values either from literature, data, locally available data, as well as we allowed the model to calibrate some of these parameters. So it's a combination. So essentially, what happens is that this model enabled us to determine certain parameters and enabled us to make more longer forecasts, which what the ARIMA model did not allow us to do. And most importantly, we were able to model the disease dynamics, meaning all the parameters in terms of incubation period, infectivity rate, transmission rate, those kind of things. However, we realized that this particular model that we developed had certain limitations to it. Now, what are these limitations? Is that it didn't factor in the temporal changes in time. As we know, whenever we deal with any pathogen, infectious pathogen, they never remain the same. That means the disease transmission dynamics tend to vary over time due to various factors. And this model was unable to do that, right? So therefore, to account for that now, we moved on to a second model, which was also a compartmental model, but this time, the compartmental model was primarily functioning to account for the effect of variation in disease dynamic that would occur over time. And how did we do that is basically we applied a time varying function into our transmission rate, right? So by doing so, in addition to the 3 strengths that I've mentioned earlier, we are now able to do this. We are able to model the changes in the disease dynamic, which was represented by the R value, which is, what is R value? R value is an indicator or a matrix to measure disease transmissibility over time. Simply put, how many people would get an infection upon exposure to an infected individual. So if you can see, this point here was the limitation or the shortfall of our previous model, and now by accounting this time varying element into the model, we are able to address that limitation. However, we realized that this model, although it was able to account for the dynamic changes in disease transmission over time, it still lacked certain degree of validation. Okay, we need our models to be valid to be able to produce outputs or forecasts that are accurate. So now, what did we do? Now we know our compartmental models are able to account for the disease parameters, the disease dynamic parameters. They are able to account for transmission dynamic that changes over time, but they lacked validation. So in order to fill in this gap, we applied a probability modeling concept to the existing compartmental models. Now, what is this all about? Simply to put it in a nutshell, basically what we did was we used a Bayesian framework. This is a statistical analysis. Okay, this is a complex statistical analysis that basically runs the model multiple times using a range of parameters that we have preset. And in this case, the Bayesian framework actually ran for a duration of 20,000 cycles, and it identified which were the most accurate and suitable parameters which should be used in the model. And you can see this graph here, which is on the right hand side, is an example of a posterior distribution which was done using the Bayesian framework with its credible limits, upper and lower limits, and it allows us to identify which should be the most appropriate value that we can use as a transmission, as a rate to move our state variables. So at this point, we are at least certain that we are using parameters that have been validated through a robust method using the Bayesian framework. Now, having done that, we then realized that yes, we were able to develop models that are valid, but now we want to factor in external factors that could change the dynamics of disease transmission. And in this case, as my previous colleague, Dr. Ain, has mentioned, there could be multiple factors, things like non-pharmaceutical intervention, movement control orders, and vaccination. And at that point of time, one major factor that we were very interested to see is how vaccination actually influenced the disease dynamics of COVID-19, right? And for that, we then developed compartmental models that were able to account the effect of vaccination. As you can see here, we used the basic SEIR model. But what's interesting about this model is that we wanted to account the effect of vaccination. So how did we do this? First, we determined at that point of time, the ministry had a target to achieve 80% vaccination either by the end of October or by the end of December. So what we did was basically we plotted the daily rate at which the vaccination should be, as you can see in this graph on the right hand side, to achieve those two targets. And we came up with two equations, and we included these two equations into our compartmental models. So now this was applied on the state variable, because as we know, the basic concept here would be this: individuals who have been vaccinated. I have to make it very clear that this model has an assumption saying that individuals that have been vaccinated are basically free from, would not be susceptible any longer to the disease, but that is a model assumption. So having said that, now we are able to account for the effects of vaccination through this method of accounting the rate of vaccination. So 4 models were developed over time. Now we were very much interested in moving on into the next step. And what is the next step? We know that R value is a good measure of disease transmissibility. This R value can be generated using the compartmental models. However, if it were to be generated using the compartmental models, is where it requires a lot of computational power, it can be time consuming, and you may have difficulty in getting the R value on a real-time daily basis, which is something we really needed, because we wanted to know what is whether the R. So let me just share with you. In essence, the R value if R value is more than 1, it would indicate that the disease is going to keep on transmitting. If the R value is less than 1, it would indicate that the transmission would eventually die off. So we needed that piece of information. We know already that our compartmental models were able to estimate the R value, but now we want to use a more, I would say, efficient way of estimating it. And for that, we used a statistical algorithm that has been previously published by an author called Corey et al., where this statistical algorithm actually uses the serial interval method to estimate the R value. So we used that algorithm using certain parameters. We generated the R value using the statistical algorithm. Now that was basically the step 2 that you are, that is a step 3. So if you can see the step 1 here step 1 is, you can see, is we have generated the R value using our compartmental model. The step 2 was what I mentioned previously. We have validated those values using the robust Bayesian inferential framework. Step 3 that you see down here is actually now we using the Corey et al. Statistical algorithm value to generate the RT values. So now we have 2 systems that have generated daily RT values. One is the compartmental model, step 1. One is the step 3, which is the Corey et al. Statistical algorithm. So the rightful thing to do next is to basically correlate these 2 values to see how well they correlate, and that is where we go to the step 4. And you can see here you have 2 lines. You have got the black line and the red line, wherein the black line are the R values that have been generated using the statistical algorithm, and the red line is the R values that have been generated using the compartmental model. And we found that these 2 values correlated very, very well. Strong correlation, 0.91. And at this level, we were quite confident and quite sure that now our daily R values can be estimated using this statistical algorithm, which we have validated. Now, hence, what we did from here is we developed a dashboard. As you can see, this is a dashboard. And this is a dashboard which is very informative and a very interactive dashboard which does many, many things. Number 1, this dashboard produces daily real-time RT value for COVID-19 at a national level as well as at a state level. So as soon as, for example, the day's data of COVID-19 cases comes in, we are able to estimate the RT value for that day. And this is very much helpful. So you can see, this is what I was mentioning earlier here. You can see that this is the RT value plots. And you can see this is 1. 1 is basically the threshold. And if you have got R values that are going more than 1, we would anticipate cases would tend to rise up. And if you have got R values less than 1, we would anticipate cases to gradually go down. So basically, this was a dashboard that we had developed using that statistical algorithm that was able to produce real-time automated daily COVID-19 RT values. So just to share some of our outputs, when it came to the second wave, we developed, using the previous models, we developed the COVID-19 forecast. So let me just share this with everyone here. So our model basically had forecasted that you have got two graphs here. One, you have got a blue graph, which is a graph that how cases or the trajectory or forecast of cases would occur if SOPs were to be followed, and one if SOP were not to be followed, right? So we provided this forecast much earlier in hand using those methods, and we can see that based on the forecast, the SOP practices were continued, and thankfully the cases fell well within the blue trajectory. All right, this is an example. Then we also have got a compartmental model that provided a forecast of a possible fourth wave of COVID-19. As you can see here, this was the forecast that was produced at this was where the model produced the forecast at this point in time, saying that if we continued our current practices, our current control measures, our current SOPs, we would expect cases to come well within this blue trajectory. But if we do not, then they would take the red trajectory. And as you can see, what happened in the subsequent weeks is cases actually started to rise, all right, following the red trajectory which had occurred. And we had forecast this much earlier. So these are some examples that show you how compartmental models are able to provide fairly accurate forecasts with the usage of good disease dynamic parameters and factoring in the valid models with time-varying effects. So, and let me just move on to the fourth wave. So this is very interesting. This is where we accounted for the effects of vaccination. So here you can see that this is our compartmental model forecast. So at this point in time, we provided a forecast. One you can see is a blue forecast here, and one is a orange forecast. So the blue forecast is a forecast assuming that we have achieved 80% of our population completed these 2 doses of COVID-19 vaccination by 31st October, and the orange one is by 31st December. So these were the two timelines that were given. So of course, naturally, if we are able to vaccinate people faster, we would assume that the pandemic or the outbreak would basically come down much quicker. So here there are two important things. Number one, we are actually forecasting when the outbreak will possibly peak and when would it possibly end, right? So this is what was given earlier. And at this point in time, we said that the cases should peak somewhere between 25th August to 15th September with an estimation of about 18 to 24,000 cases. Now, what had happened in the subsequent weeks, we can see clearly that the observed case trends that occurred, okay, were very much close to the forecasted produced in the blue curve. So we can see that what happens is the model forecast was cases was supposed to peak on the 25th to 15th September with about 18 to 24 cases. And what actually happened was the highest daily cases or the outbreak actually peaked on 26th of October, which was actually one day past our forecast peak. And the case range at the maximum was about 24,599, which was also within the given forecasted peak number of cases. So this shows that the model can actually be fairly accurate, fairly reliable if it has been parameterized with the right variables, if it has been validated robustly, if it has also factoring in effects of time-varying parameters, and you account for the effects of intervention. So just to end it up, these are several, we did participate in several innovation competitions based on our models that we had generated. And we did actually win several awards, which is, for example, this is in the Malaysia Technology Expo. We actually won a gold medal and an award merit, and this is for actually the R dashboard that we had developed. And these are some additional achievements. So, so with that, this is all about compartmental model. I'll pass it back over to our moderator, Dr. Balvinder.
Oh, thank you, Dr. Sarbhan, for a very, very comprehensive presentation on compartment models and excellent presentations from Nur'ain on the ARIMA models. Both presentations were I would say, the best I've heard. Okay, so without in the interest of time, I think we'll move on to some Q&As. We have a whole load of questions already in the list. So I'll start with the first question, which will be directed to Dr. Nur'ain, which will be on time series models. So the first question is, how can time series models help in early detection and response to emerging infectious disease outbreaks?
All right, thank you for the question. As what we have learned before, as what I've showcased in the slides, once we make a forecast of a case, it comes off together with a forecasting interval. Usually, there's two intervals that will be given in the programming language. The 80% confidence interval and also the 95% confidence interval. So how you can use this model, this forecasting model, to detect early possible outbreak, you can actually compatible and the forecasting trend. If you see some deviation of the forecast value against the what you are having right now, then it's possible that you can say that there's a possibility of a new outbreak. So you just have to look at it, where it actually intersect, whether it goes off whether your forecast go off of the confidence interval, then you can actually say it is possible that you may have a possible outbreak.
Thank you. Well, it's interesting that you can actually do this forecasting. It's like, being almost a magician, that we can foretell the future, and that's where I find that this is something not only it's almost magical, but it's actually it's based on methodology, statistics, etc. So there is a method to it, that what we are forecasting is just not some random prediction. And the next question, I'll pass it to Dr. Sarbhan, where it's quite an interesting question, is what assumptions are typically made in a compartmental model?
Thank you, Dr. Balvinder, for that question. Actually, before I answer that question, I would like to share that I've learned a lot of modeling from Dr. Balvinder, and when I noticed that he present his slides, the first few slides that he always present is not all models are correct. Some are useful. Yes. Some are useful, and that saying till today stuck strong to me. And many a times when we work together, Dr. Bal always puts in the need for an assumption. Why? It's because models are never going to be true. They can predict, yes, but to a certain extent. And for that, you have to have certain assumptions to sort of make your model applicable. So I'll give you an example, as I've mentioned earlier. So when it comes to infectious diseases modeling, one assumption that you can clearly make, if you would like to make so to make your model less complicated, is that you can make an assumption saying that those individuals who have received some form of treatment or some form of intervention are no longer susceptible to a particular disease. Now, this is applicable depending on what disease you are talking. Of course, some diseases, once you are treated, you may not get it. Some, you may get it. And if your model is doing such a thing, then you have to make an assumption and make it clear. And why? Because when you make that assumption, then individuals who have been removed or treated from your model, they no longer will backtrack into the susceptible compartment. So that is one example. Similarly, assumptions, there can be many. We applied many assumptions in our models with regards to possibility of reinfection, factoring in the time-varying change. So to me, I feel assumptions are important. They safeguard your model, but you must make it clear and you must justify why you have put these assumptions in place. So I feel that's my opinion on it.
Oh, right. Thanks, Dr. Sarbhan. See, the word assumption itself it tells you is we are assuming. So it's assumption usually made based on some indications, some observations, and are not just random assumptions which doesn't hold good or doesn't have anything to hinge on it. And true enough, most of the assumptions we make also is those which, after observing past outbreaks or similar sort of situations that we would expect. For example, the one on the vaccination, that most vaccinations would reach a peak at one point, and then it will slowly, individuals will not be so keen to take the vaccine, and you will take longer to reach the last part.
Exactly.
So which basically it's an assumption based on regular how vaccines are administered.
Given.
So that way, those are the kind of assumptions I think which we have used
Valid assumptions.
Valid assumptions. So I think this would be the last question. Are we good for time here? Because the last one will be, I think, for both of you all, and I think it's a question to argue out which is a better model, the pros and cons between ARIMA and this compartmental models. So and then we will let the viewers judge which is a better model.
All right. Which is the better model, time series or a compartmental model? Let's take COVID-19 as our use case. In COVID-19 is a novel disease. It's a new disease. For time series, and I think that's why actually we started off with time series model instead of compartmental model with COVID-19, because as I said before, time series model, you basically model the data based on your autocorrelation, based on your trend. So basically it is actually based on your past data. It does not account for any disease dynamics like compartmental model. You need to know the infectivity rate, the recovery rate, whereby we know that during the initial stage of the COVID-19 pandemic, there was no information about that. There's very little journals, and we basically have no information for that. So because of that, we actually started off with time series. So I think the strength of time series, if you have an adequate amount of time series data points, I think you can start it off with a time series. I mean, there's always the strength of limitation for every model in this world, but as I said before, it depends on what kind of model that you want to actually model, what type of data. So you have to pick and choose and look which model best suit for my data.
I think Dr. Ain has just mentioned everything that needs to be said with regards to Dr. Bal's question. Both models are important. Both models are essentially useful. As a user, it's up to your circumstances, so your current context, what data you have, what you're trying to achieve. You can pick and choose accordingly.
And I don't think you all argued enough to say which one of your model is better. However, I think that the true fact is what you have mentioned. It's actually a quotation by Box Jenkins, who would be considered the father of modeling, which is all models are wrong, but some are useful. But I would like to emphasize at the end is that all models are useful, and if we use it right, there's a lot of uses for it, and we can actually use it for prediction, prevention of infectious disease outbreaks, and like what we did for COVID. So with that, I think we have reached our time, and we thank our speakers again, and we wish that everyone had a interesting, enjoyable, knowledgeable take from modeling. And if you all do need more information, we are always here to collaborate and discuss further. Thank you very much for your time, and we will meet again for the next CME for NIH. Thank you.
Thank you.